Dear students, in this session we will discuss the p-value approach to hypothesis testing. To introduce the p-value approach, we again use the example, the claim of Jean that his driving distance is 275 yards. 275 yards and he hits 25 times the ball and x bar is 264.4 obtained from n is equal to 25. The same example, and we fix alpha at 5%. The level of significance as usual 5%. Now H0 is mu is equal to 275 versus H1 mu is less than 275. So the question is, do the data provide sufficient evidence to conclude that mu is less than 275? And we assume that the driving distances are normally distributed. Standard deviation of the population is 20 yards. Standard deviation is 20 yards. Driving distances are normally distributed. And the test statistics is Z as usual, x bar minus mu of x bar by sigma by root n is equal to x bar minus mu by sigma by root n. That is x bar minus 275 by 4, the test statistics. Now, the hypothesis test is left-tailed. And as the hypothesis test is left-tailed, we compute the probability of observing value of the test statistics Z, that is as small as or smaller than the value actually observed. The value actually observed, when we substitute the values here, the value we actually observed was what was the value? It was minus 2.65. The value of Z actually observed, substituting the value of x bar, was minus 2.64. Now what we do is, we ask a question. What is the probability that Z is equal to minus 2.65 or less? What is the probability that Z is minus 2.65 or less? Remember this. If the Z distribution is given, then minus 1.96 plus 1.96. If I ask a question, what is the probability that Z is equal to 1.96? The answer is 5%. Probability that Z is equal to 1.96 is 5%. Then what is the probability that it is equal to minus 2.65? This probability is less than 5%, 5% or 0.05. Let it is equal to 0.004. That is the probability that Z is equal to minus 2.65 or less is 0.005. And this probability is called the p-value. This probability is called the p-value. So what is p-value? P-value is the actual probability of observed value of the test statistics. Actual probability of obtaining the observed statistics. The observed value of the statistics is minus 2.65. And what is the probability of observing a value equal to minus 2.65? Let it be 0.005. That is 0.005 is the actual probability of getting the observed value of the test statistics, and this probability is known as the p-value. And if the value, then the decision is, if the p-value is less than or equal to the significance level alpha, then reject HC. If p is less than or equal to alpha, alpha is the level of significance. In our case, p is equal to 0.005, it is less than 0.05. 0.05. Then we reject H0. As the p-value is less than the level of significance, we reject H0. So, we obtain the p-value of the observed test statistics and compare with the specified significance level. And if actually it is 0.004, that is probability of Z equal to minus 2.65 is or less is 0.004, and as p is less than the level of significance alpha 5%, we reject H0. Now, if H0 is true, we would observe a value of the test statistics only 4 out of 1000 times. 0.004 means 4 out of 1000 times. Not 5 out of 100 times. So, let me give a definition of what is p-value. P-value of a hypothesis test is the probability of getting a sample data at least as inconsistent with the null hypothesis as the sample data actually obtained. And the smaller or the close p-value to 0, the stronger is the evidence against the null hypothesis. As p-value becomes increasingly small, it is strong evidence against null hypothesis. And this p-value is also known as observed significance level. Observed significance level. It is the smallest level of significance in which a null hypothesis is rejected. If alpha is 5%, that is the significance level, 0.05. What is the observed significance level? Observed significance level is 0.004 in our example. And it is the lowest level of significance in which a null hypothesis is rejected. Lowest level of significance in which a null hypothesis is rejected. It is when we reject a null hypothesis, as per the critical value approach, we will be committing 5 mistakes out of 100. But the actual probability of committing type 1 error, reject H0 is true, is only 4 in 1000, not 5 in 100. So, the p-value of a hypothesis test equals the smallest significance level in which an H0 can be rejected. That is, the smallest level of significance for which the observed sample data results in the rejection of H0. And remember this, the determination of p-value is very simple. As usual, we formulate H0 and H1. Sigma is assumed to be known. variable is normally distributed, everything is there. We calculate the test statistics. We have the value of the test statistics. And if the value of the test statistics is less than the critical value, if the value of the test statistics is less than the significance level alpha, then we calculate the p-value, the probability value associated with the observed value of the test statistics. And if this p-value is less than or equal to the level of significance, reject H0. Whether it is a one-tailed test or a two-tailed test. And if p is greater than 0.1, evidence against H0 is weak or none. Weak or none. If p is between 0.5 and 0.1, moderate evidence. If p is 0.01, 0.05, between, strong evidence. If p is less than 0.01, very strong evidence. Very strong evidence. And actually, in applied research, statisticians will not, consider significance level. They calculate the value of the test statistics and report the corresponding p-value. Suppose that Z is equal to 1.96, then p is 0.05. Suppose that Z is equal to, as this example, minus 2.6, etc., then it is 0.004. Suppose Z is equal to 10, you will get almost equal to 0. So statisticians report the p-values. Then you can take a decision about accepting or rejecting a hypothesis. Suppose that p is equal to 0.07 as an example. At 10%, you cannot reject H0. Sorry, you can reject H0, but at 5% you cannot. So it is your decision whether to accept or reject H0 at 5% or 10%. 0.07 means if alpha is 10% or at 10%, or when you reject a hypothesis, you are committing 7 mistakes out of 100. You will be wrong 7 out of 100 times. If a p is equal to 0.10, you will be making 10 mistakes out of 100. It is your decision whether to reject or accept H0 at 1%, 10%, 5%, etc. So applied researchers simply report p-values and you can take a decision about accepting or rejecting hypothesis. If you want very much a precision, very strong evidence against H0, p equal to or less than 0.1, or suppose that p is equal to 0.07. Then if alpha is 5%, you are not tolerant to more than 5 mistakes. 0.07 means you accept H0. But if alpha is 10%, you reject H0. That is the issue. And for example, if you want alpha at 1%, and if p is equal to 0.04, then you cannot reject H0. You accept it. So it depends on the precision with which you want to accept or reject H0. And remember this, in empirical analysis, generally p-value is reported. alpha is not, and we will see some more points about what is the arbitrariness in fixing alpha in advance in a later class. So for the time being, there are two approaches. One is the critical value approach, the other one is the test of significance approach. In all these cases, remember this, we have a test statistics based on the sampling distribution of an estimator. And the value of this test statistics is divided into acceptance region and rejection region. Our decision to accept or reject H0 depends on whether the value of the test statistics obtained from the sample at a chosen level of significance is in the critical region or in the acceptance region. That is the only point which you are supposed to remember. And all our procedures are based on the assumption that population standard deviation is known. And we will consider cases in which population standard deviation is unknown, where we will use, as in the case of confidence interval approach, what is known as the T as the test statistics. Again, the procedures are same. And in all these cases, what we have considered is testing the significance of one mean. And with this can be generalized into all types of hypothesis testing procedures.